Hello there, I'm John DeGoes, and today I would like to give you a tour of ZIO. ZIO is a purely functional library for doing async and concurrent programming in Scala. It lets you build applications that are testable, modular, maintainable, type-safe, reactive, and resilient, applications that scale, both literally in terms of performance and also figuratively in terms of team size and length of time spent maintaining a code base. This will be a brief introduction to ZIO. We won't have time to go into too many topics, but I do want to give you some reasons for poking around and investigating more. ZIO is a library based on fiber-based concurrency. So fibers are coming to the JVM via Project Loom, but until then, you can use libraries like ZIO to get fiber-based concurrency now. ZIO is also a library that is 100% asynchronous. So unlike some other approaches out there, all of the code that you see in ZIO is 100% non-blocking. Even code that looks like it's blocking actually doesn't block. And to the maximum extent possible, ZIO leverages the Scala type system to help you catch more bugs at compile time when they're easiest and cheapest to fix. The most important data type in ZIO is a data type called ZIO. This ZIO data type has three type parameters, REA, and I refer to it as a effect, as a functional effect. A functional effect can be thought of as a value, an immutable value, that represents a job or workflow or a task of some type. You can think of functional effects as being a lazy description of various types of interaction with the outside world, such as talking to a database or talking to a web server or printing a line of text to a console or mutating some memory or so forth. ZIO effects are 100% lazy. If you have a ZIO effect in your hands, in your program, or you're passing it around or storing it in the data structure, nothing has happened at that point in the world. You actually have to do an operation called execution in order to translate that description of interaction with the outside world into actual interaction. That's called running the effect or executing the effect. And you do that using one of the unsafe run methods. A nice mental model of a ZIO effect is as a function from this R type parameter, that's the first type parameter in ZIO, to either an E, which is the second type parameter, or an A, which is the third type parameter. So a functional effect can be thought of as requiring some environment type R. This could be a database connection or some configuration. It could be an HTTP client, could be a Spark session, could be many other things. What you use this is up to you if you even want to use it, but it's there if you like, and it turns out to be very useful in describing the dependencies between different parts of your application or threading through information that should be pervasive across your application code base. This function accepts an R, that's what you feed it, and then you get out either an E, which represents a failure of type E, or a success of type A. So functional effects can be thought of in your head as functions. You give them R's, and you get out either a failure or a success. Now this is the full ZIO effect, and you can use this for 100% of everything, but it does turn out that there are common simplifications to this type that are useful, and so ZIO defines the following 5 different type aliases. And the meaning of these type aliases is as follows. Task represents an effect that doesn't need anything, can fail with any throwable, and succeeds with a value of type A. The use of any here for the environment type is important. It allows you to model some effect that doesn't require anything at all. After all, a function that takes any, you can execute that function by giving it a string or a number or anything you want. It doesn't really care what it is because it accepts a value of type any. Throwable here we use for the error type to indicate that that's one possible outcome of executing this effect. We might get back an error. And then A, of course, is the type of success. UIO of A is an effect that doesn't require anything, cannot fail, and succeeds with a value of type A. The nothing type here is important. It represents the fact that this effect type can't fail. If you substitute in your mind either nothing here, so E equals nothing inside this mental model for a ZIO effect, then you have either nothing A. And nothing is a special type in Scala because there are no values of type nothing. There's no way to actually build a value of type nothing. So if you ever see an either of nothing A, you know that's a right of an A, because there's no way anyone could have constructed a left of a nothing. There are no values of type nothing. And in a similar fashion, when you see this nothing parameter stuffed inside the ZIO effect type, it means that effect cannot fail. RIO of R and A refers to a ZIO effect that requires an environment of type R, may fail with any throwable, and may succeed with the value of type A. IO of EA refers to a ZIO effect that doesn't need anything, can fail with a value of type E, or succeed with a value of type A. And finally, URIO of R and A represents an effect that requires an R, does not fail, and may succeed with a value of type A. So these are the common permutations of different type parameters. You can see every one of them either eliminates some feature of the ZIO effect type that's not needed, for example, eliminating the environment by using any, or eliminating the error by using nothing, or the remaining ones just fix the error type to be throwable, which is a very common type of error to use inside a Scala application. With that introduction to the core ZIO type out of the way, we can now proceed to write a hello world program. We're going to write a hello world program by extending app. App is defined in ZIO itself, and it gives us this main function. It also bakes in a runtime that's used to execute the effect that we return from this run function. The run function is provided the command line arguments to the application as a list of strings. So here we have to return some effect, and there's a way to construct an effect in here, actually several of them. The one we want to use for this hello world application is a method called puts_line. We give it a line of text, and it gives us back an effect. Now if we save this, we're going to encounter a type error. And the type error says that this effect succeeds with a value of type unit, but we have to return an effect that succeeds with a value of type int. So we've got to go from this effect that produces unit as its successful output to this effect here, which should produce an int as its successful output. And one of the ways we can do that is to map over the success and take that unit value and ignore it and return some integer status code like 0. The int returned by our effect here will be passed to system exit when our run function terminates. So this is how we communicate with outside processes that are calling into our application by using this integer status code. When we save this, it will now compile. Now mapping an effect to a constant value is pretty common, so there's a shorthand here called as. We call as0 here, and this means the same thing. Scala allows us to use infix notation, so if you prefer, you can write this as as0. In the next example, we want to do actually a sequence of print lines. We want to print one thing out and then print another thing out. Now to do this, you might think all we have to do is open up a code block and print line hello in the first line and then print line world in the second line. Now, this doesn't actually do what many think it does. This first line here builds an effect, but the effect is thrown away. Remember, effects are totally lazy, so even when this effect is constructed by puts_line, nothing has actually happened in our application other than building this immutable value. So it's as if we didn't build it at all. We're building it, but then we're not using it. We're not composing it with the return value of this function. So we're building it, not using it. We may as well just delete it. This application here is exactly equivalent to this one here. There's no difference. Now, of course, that's not what we want. We actually want to do one thing and then do something else. And so what we need is an operator that can take these two separate values here and combine them together, compose them together to get another functional effect in such a way that we do this first thing here first and this second thing here second. And there is such an operator. It's called IsItLeft. We can call it like this, or sorry, ZipLeft or ZipRight. We can use either one in this specific example. There's ZipLeft here, and then there's ZipRight. And the difference between them is that they both zip these two things together. They zip two effects into one effect to produce an effect that succeeds with a tuple of the outputs of left and right. And then ZipLeft, what it does is it returns the thing on the left-hand side and throws away the thing on the right-hand side of that tuple. And ZipRight does the opposite. It throws away the thing on the left-hand side of the tuple and gives you the thing on the right-hand side of the tuple. Now in this case, we're going to get out a unit from here and a unit from here. So when we zip left or zip right, it doesn't matter. We're still going to get a unit, and we don't even really need the unit, but we have to return something. Now there's a symbolic operator here that turns out to be quite handy. I'm going to start using that. ZipRight is written star greater than, and it allows us to write this code as follows. And then once again, we need to return a single value of type int here. So we can do as 0. Or there's one other thing that we might want to do in this particular case. Do another ZipRight, and then construct an effect that succeeds with a value, which we can do with ZIO.succeed. So what this will do is it will print out this, and then it will print out this, and then it will construct this effect that succeeds with 0 and return the 0. In our next example, we're going to look at error generation and error recovery. You can see here I've constructed an effect called failed. And this effect called failed is actually the composition of three other effects. This effect, and finally this effect. So we're composing these using the ZipWrite operator. And this builds a composite effect that describes the sequence of these individual three effects in order. Now, as in any programming language, ZIO features short-circuiting error handling. So when you go to execute this effect, what's going to happen is it's going to print out this, and then it's going to move to this line and fail, and then the entire process, the chain of operations will be interrupted, short-circuited, until someone at a higher level ends up catching that error. Note that we're failing here with a string. We could actually fail with anything we want, a custom error type, or an integer status code, or a throwable, or an exception. It's up to us. ZIO features polymorphic error channels, so we can use that to our advantage. In this application, what we're going to do is call failed, and we'll try our normal trick of calling as 0 to get it to compile, and we see that it doesn't compile. And it doesn't compile because the Scala compiler knows that this effect here can fail for some string reason. That's the middle type parameter here. Whereas the effect that we return from run has to be infallible. It should not be able to fail. So what the Scala compiler is doing is it's saying, hey, you forgot to handle your error. You need to convert your error into this status code so other processes know how to interpret it. And this is a good thing. This is an advantage of using typed errors like ZIO gives us, is that we can define in type signatures what our error handling behavior should be, and then the Scala compiler can be our friend and help us direct the implementation into such a form as it satisfies our requirements expressed in types. Now in this case, what we would like to do is, if this fails, and we know it will, we will simply exit the process with a status code of 1, indicating there was some sort of failure. And we'll do that using the or else operator. The or else operator is this type of fallback operator. It's going to try to do this effect, but if it fails, it's going to switch over and try to do that effect. Now, This effect can fail with a value of type string. This effect cannot fail. So the composition of these two effects cannot fail. And at this point, we've proven to the Scala compiler that the effect that we're building here is infallible. And so we're allowed to return this. We've properly handled our errors. Now, another way to handle this would be to delete everything, start back from failed, and try to handle both error and success at the same time. You can do that using a method called fold, which also exists on either and other data types in Scala. And we give it an error handler and a success handler. The error handler will return 1. The success handler will return 0. And finally, the last way I'll show you of handling this error would be to take this failed, convert its success value to 0, and call catch all on it, which allows us to catch all the errors. And actually, I'll call the most powerful variant of this, which is catch all cause. And this will actually give us a causative string, not a string, but a causative string. The string is coming from the fact that this effect here fails with a string. The cause is coming from ZIO. I'll explain that in a second. And what we'll do when we get this is we'll call putStirLine, and we will call cause prettyprint to render that cause nicely. And then we'll do an as one there to indicate that we failed. So this cause data structure is a wrapper on the error. And this wrapper on the error actually embeds some very powerful features in it. ZIO features a lossless error model that never loses any information. So as our computations are composing in parallel and maybe with async regions and maybe with finalizers, when things go wrong, ZIO keeps track of the full story of what happened, which means that if two things failed in parallel, we'll get back both those errors. If one thing failed and then on the way out, a finalizer failed, well, we'll get that error as well. We'll get all that rich information inside the cause data structure. And not only that, but the cause data structure will contain what's called an execution trace. Fiber-based systems, and even last generation systems like Scala's Future, they spend a lot of their time executing async code. And one of the bad things about async code is that you don't get stack traces. Stack traces are useless. If you print out a stack trace from a Future, you'll find that you see the insides of Future and the fork join thread pool, but not much else. ZIO is the only effect system that features a execution tracer that actually reconstructs information about where the failure occurred. And that execution trace is inside here. So when we print this out, we're actually going to see this line here, line 37, and this line here, line 38. We're going to see the full execution trace, very, very detailed, much more granular than the level of every method. We're going to see sort of line by line execution trace. And not only will we see that, but we'll also see where the code would have gone, where it would have executed something, some other effect, if it hadn't failed. And this gives us enough information to very quickly diagnose problems in production. This is one of several features that allows ZIO to be very productive when deploying real-world applications using modern fiber-based concurrency systems. Another key one is the fact that ZIO allows you to do what's called a fiber dump, which is like a thread dump, but for fibers. It shows you the state of all the fibers in the system, whether they're running or paused, and whether they're blocking on some other fiber or not. In this next example, I'm going to show you how to use recursion to implement a form of looping. So here we have this repeat function, which accepts an effect and returns an effect. And it also accepts a number here, n. And the intention is that repeat should take this effect and repeat it the specified number of times. Now this is possible to implement precisely because ZIO is completely lazy. You couldn't implement something like this for Future because at the moment when you have a Future, it's already running and there's no way to restart it. So you can't write combinators like this, which means that Future is not very powerful or expressive, and there's many kinds of duplication that you simply can't abstract over. But with ZIO, because everything is nothing more than an ordinary immutable value, just like a Scala collection, you can write combinators that accept effects and return effects. And here we'll do that. First off, if n is less than or equal to 1, we'll just return effect. Otherwise, we'll return effect, zip right, repeat of n minus 1 on effect. And if you run this, you'll see it prints out this line of text 100 times. It's taking this piece of this effect here, and it's actually zipping right with itself many, many times, 100 times. In this next example, we're going to implement an interactive application. What we would like to do is ask for the name of the user, read it, and print it out. And we can do that using functions inside console. So this part is straightforward enough. We ask the user for their name, and then zip right, and we can call getStirLine to get the name of the user, get a line of input from the console. And then we could call zip right again, and what we would want to write is something like putStirLine hello name. The problem is a name isn't defined anywhere. And that's because even though we did read a line of text from the console, we weren't able to give that a name using the zip right operator. So if we want to do several things in sequence, and what comes after depends on the return values, the success values of what came before, then it's not sufficient to use zip right. We actually need to switch over to using an operator called flatmap, which is also known as chain and sometimes and then in other programming languages. Using flatmap, we can specify a success handler, and this success handler gets to accept the success value from this effect and produce another effect based on that success value. Now, if you have multiple flat maps in sequence, then they end up nesting in the following fashion. Here we would put a flat map after this putStirLine, and then that would create another nested scope. And then if we wanted to do something after that that depended on what came before, we would create another level of nesting and so forth. Now that doesn't actually read very well, so Scala has 4 comprehensions, which let you clean this up some. How we would write this same logic using a 4 comprehension is as follows. And how this is translated by Scala is it's a call to putStirLine followed by a flat map. The success handler will name that parameter underscore because it doesn't care about the unit value that's returned by putStirLine. And then it's going to return the rest of this. And in the rest of this, the first thing it's going to do is call here and call flatmap on it. And the success handler, it'll name that parameter name, and then it's going to return the rest of this. And then in the final line of the 4 comprehension, it's going to call this, and then it's going to map, not flat map, but map over this. And it's going to name that parameter in the success handler underscore. And then it's going to map that to the constant 0. So we'll get 2 flat maps followed by a single map. In general, if your 4 comprehension has n lines, then you get n minus 1 flat maps followed by a final map. In this form, it's a little easier to read what's going on, and you can sort of see the linear structure. Each one of these lines resembles a statement. And it is unfortunate that we have to name these underscores here, even though we're not using them, but that's just the way this thing works. In Number Guesser, we're going to implement a number guessing game, very simple number guessing game. And how we're going to do that is we will first guess a random number by using a method in here that constructs an effect that succeeds with a random number. We'll guess a number between 1 and 3, and we'll print out a line of text to the user saying, Please guess a number from 0 to 3. We'll get the guess by using getStirLine. And finally, we'll call this analyzeAnswer with the random number and the guess, building 0, or else succeeding with 1. In this application, we're going to take our first look at the fiber-based concurrency model that ZIO supports. A fiber can be thought of as a lightweight green thread. Unlike threads, fibers don't consume operating system level threads. They use threads, but there's not a one-to-one mapping. In general, one operating system level thread will end up running lots of fibers, maybe hundreds, maybe thousands of different fibers. Fibers also are non-blocking. So because they support asynchronicity, anytime they're waiting on something, they just suspend, not actually consuming thread resources. And then when the thing they're waiting for is available, then they resume. This allows fibers to be very, very efficient. They also have growable and shrinkable stack sizes, unlike actual threads, JVM level or operating system level threads. And they can be garbage collected automatically if they're suspended and they can't be reactivated. So in this example, what we're going to do is leverage a few different helper functions. This one here tries to parse a string into a double and returns either a number format exception or a double. GetAlarmDuration is an effect that could fail with an IO exception, or it could succeed with a duration. And it's implemented as follows. First, it tries to parse the first thing it does inside the for comprehension is print out, please enter the number of seconds to sleep. It reads that as a string, and then it calls parse duration on that string, which tries to parse that into a double, and if it succeeds, it maps it into a duration. Then we take that either returned by parse duration, and we convert it into a ZIO effect by using ZIO.fromEither. And then if that fails, we execute a fallback, namely this fallback, which consists of two effects in sequence, putStirLine, you didn't enter the number of seconds, followed by getAlarmDuration. So this effect in its definition actually refers to itself. It is a self-referential effect. And that creates the effect that if the user enters some bad data, they didn't enter some number of seconds, then it creates a loop until they enter good data. The first thing we're going to do inside the main function is we're going to call this getAlarmDuration so we can get the duration back. And then for pass number 1, what we're going to do is we'll call ZIO.sleep on this duration. And finally, we're going to print out time to wake up. And we'll yield 0. Now this is a linear chain of these three different effects. And this one is a loop, an interactive loop that's going to keep on working until it gets some valid data from the user. And then this one here is going to sleep. This looks like it's going to block, but it's actually not. It's purely asynchronous. And then after it sleeps, it's going to print out the final line. To make this a little more interesting, what we're going to do is we're going to print out little dots every second while the user is waiting around for the alarm to go off. And to do that, we're going to see a fiber. We're actually going to construct a fiber. All code in ZIO runs inside a fiber. In this main function, there's currently one fiber. That's the main fiber that executes this effect. What we're going to do is create another fiber. And we're going to do that because we want to print out dots at the same time as we're sleeping. We want one fiber to be printing out dots, and we want this fiber, the main fiber, to be sleeping, so that after it's done sleeping, it can continue with this message. So in order to do that, what we're going to do is call putStir, print the dot character, and then what we're going to do is sleep for a second. And we're going to take all of this and repeat it in a loop forever and ever and ever. We can do that by calling the forever method on a ZIO effect, which will take this effect and return one that does the same thing over and over and over and over until it fails. You can see what I get out of here is a ZIO effect that cannot fail and it cannot succeed. It's just an endless loop that can't fail. I don't really want that though, because if I execute this code now, this line of code will never happen. I get stuck here. What I want to do is take this effect and run it in a different fiber. And I can do that by forking this effect. And when I fork this effect, then now I get back a fiber. And this fiber here has two type parameters. This is the error type and this is the success type. This tells me that this fiber here can't fail and it can't succeed. So now I have this fiber running in the background, and I can go ahead and sleep and continue after this line. I can continue and sleep and then print this wake up message. And then when I do print up the wake up message, what I also want to do right after that is take this fiber here that I forked in this line and interrupt it. I call interrupt here. Or a more compact way to express all this, rather than using all these underscores, would just be to use the zip right or zip left operators. So now I have this nice little progress tracker, which is running as a separate fiber, and I shut that fiber down right after I print up my wake up message. Fibers are very easy to use. They're as easy to use as threads. Now they are low level, so if you can avoid using fibers, you definitely should. You should try to use higher level constructs for parallelism and concurrency, because they bake in very safe semantics, so you don't have to think about using them. You can just use them. Fibers are much lower level, so you have to think harder about using them. In this next example, what we're going to do is see some more fibers, and what we're going to do is compute pi in parallel. One of the ways you can compute pi is you can pick a random point inside the unit circle, and you can keep track of whether or not that point is inside the circle or outside the circle. And then you estimate pi by computing the fraction of randomly chosen points that were inside the circle, and then multiplying that by 4 to get pi, which would be the area of the unit circle, where the square represents 1/4 of that circle. The inside circle function is a simple test of whether or not a point is inside a circle, the unit circle. Random point just calls next double, which is defined in ZIO random, and zips that together with next double to get back an effect producing a tuple. So we get back a tuple of double double there. This update once function uses a ref. A ref is ZIO's version of a var. And the difference with var is that first off, we can interact with refs using ZIO effects. So when we get and set them and update them, we get back ZIO effects. So they're lazy and they compose well with the rest of ZIO. But not only that, a ref is actually a better version of a var, because refs can be updated atomically and consistently and in an isolated fashion without any locking. It's a similar idea to something like Java util concurrent atomic reference. It's a reference that can be updated atomically. And we're going to utilize that here because we're going to have many fibers potentially all updating the same state, the same pi state here at the same time. And we don't want them to be clobbering each other. We want everything to happen atomically, consistently, and isolated. So we're going to use a ref there just for the concurrency benefits. So what we do is we generate a random point. We extract that tuple out as an x and y. And then we compute a delta to increment the inside by. Our delta will be 1 if it's inside the circle, otherwise it would be 0. So if it's 0, we won't change it. If it's 1, we'll change it by 1. We'll increment it by 1. Then we call ref update, and we pass the update function. Everything from this paren to that paren will be done in an atomic, consistent, and isolated fashion. So we get the old state, and we produce the old state by adding the inside delta to it and adding 1 to the total right here. This print estimate method takes a ref of this pi state, gets out the value from the ref and just prints out an estimate of pi at that point in time. So we'll tie all this together in the main function. Well, first we need to make a ref. We can do that using ref make and specify the initial pi state as containing zeros for both elements. Once we've made the ref, we can go ahead and call update once. So we're going to make a worker here by calling update once on ref. Now this makes a worker that does a single update. It computes a single random number and updates the state just one time. But we need it to be doing it forever, so we're going to call .forever on there to get a worker that's just going to do the same thing over and over. And we want to do this really in parallel. So what we need is a bunch of workers. So we have one worker. How do we get a bunch of workers out of one worker? Well, we can use any method we want. I'm going to use listFill to generate, say, 4 workers. Now we have a list filled with 4 workers. Remember, because ZIO effects are nothing more than ordinary values, you can treat them as values. And that means you can create new workers, in this case, merely by replicating those workers across a list. Once we have created these values here, we're going to proceed to calling a method in ZIO that allows us to fork all of these effects inside this list and get back, basically fork every single effect into its own fiber, and then take all these fibers and compose them together to get a synthetic or composite fiber that allows us to control all of those fibers at once. So how I'm going to do that is I'm going to call ZIO fork all on the workers. And that gets me back this fiber that cannot fail and succeeds with a list of nothings. And that just represents the fact that this fiber here, it's never going to fail. It's never going to succeed. So we shouldn't try to wait for this fiber to succeed or fail. However, we can interrupt it, and we will do that later. So at this point in our for comprehension, the main fiber has kicked off all of these 4 worker fibers. And now we can control all of them as a single sort of logical fiber using this fiber reference. What we want to do, though, is we want to print out estimates over time. So let's do that in the next line of code. We'll create like a fiber2 that's going to be nothing more than put stir of a little dot. No, sorry, we'll print out the estimate here. And then we'll sleep for 1 second, call forever, and we'll fork that. So now we're printing out an estimate of pi every 1 second. And then finally what we'll do is we'll ask the user to press any key to continue. And we'll read a line of input from the console. And after we read that line of input from the console, we're going to interrupt fiber 1, we're going to interrupt fiber 2. So we can terminate these infinite computations here and all of these workers at once just by calling interrupt here and here. Or if we wanted, we could zip these 2 fibers together to create another composite fiber containing both of them and just interrupt those a single time. So there we have it. We have a program that this will use up to 4 cores on the machine. It'll work in JavaScript as well. ZIO doesn't actually require more than 1 thread. However, if you do have 4 threads, then it'll utilize, or 4 cores, it'll utilize all 4 of them, estimating the value of pi in a parallel fashion. What happens is if you specify level of parallelism not supported by the platform, let's say you're running on Scala.js, then ZIO's scheduler does cooperative yielding, making sure every fiber gets a chance to execute its effect, switching back and forth between them in a fair fashion. In the next example, we're going to look at what would be a very hard concurrency problem if we were utilizing classic concurrent primitives like actors, for example, or perhaps locks and condition variables. This is the dining philosophers problem. And the setup is as follows. We have a round table filled with a certain number, say 10 philosophers, and between every pair of philosophers is a single fork. And what we want to do is feed everyone at the table. However, every philosopher needs 2 forks to eat. So that means that every philosopher is going to be trying to acquire 2 forks and then eat their food. And then when they're done, they're going to put the forks back down and maybe someone else can try. Now, this is challenging because we have many pieces of mutable information. We have all these different forks lined up around the table. And ideally, what we want to do is parallelize it. So we want every philosopher to independently be trying to eat. And so we have many either threads or fibers all trying to eat at the same time and update the state of all these different placeholders that contain the forks. And the reason why that's challenging is because you have to think very carefully about race conditions, and not just race conditions, but deadlocks. If you pick up one fork by acquiring a lock and then pick up another one by acquiring a lock, well, suddenly you're in a situation where you're probably going to deadlock if those locks are acquired by other threads in a slightly different order. You can end up deadlocking. So ZIO STM stands for Software Transactional Memory, and it allows you to specify at a very high level what you want to execute in the context of a transaction. And this transaction will give you atomic, consistent, and isolated guarantees across many different bits of shared memory in your application. This is the difference between STM and ordinary ZIO-ref. Ordinary ZIO-ref gives you those guarantees in the context of a single reference, but you can't do multiple operations across multiple references without using ZIO STM. STM has proven itself to be an extraordinarily adept tool for solving concurrency-related challenges in functional programming languages like Haskell. And ZIO STM is sort of the first real industrial-grade, functional-oriented software transactional memory solution for Scala. The setup of the problem is as follows. We have different forks, and every fork is identified with some sort of number. We have placements, which consist of a left and a right placement. And these placements are not refs, but they're T-refs. A T-ref is a transactional reference. So unlike ordinary refs, which give you only that sort of atomic guarantee on the contents of that, T-refs have composable transactionality. You can modify many T-refs all in the context of a single transaction. That transaction type is called STM. And STM has 2 type parameters, the type with which the transaction can fail and the type with which the transaction can succeed. Anytime you do anything on the T-ref, like getting or setting it or updating it, you get back a transaction. And transactions compose, STM composes, with map and flat map and zip write and all the other similar methods that you've seen on ZIOFX. So this placement contains 2 references, each holding an option of a fork. Why an option? Because sometimes there's a fork sitting down there between 2 philosophers, but sometimes there's not if one of those philosophers is using it to eat. So that's why it's an option. The round table consists of a vector of a bunch of different placements. This is the operation that we have to implement, which is called take forks. All we have to do is we have to take this fork and return a tuple of these forks inside a transaction. Here's one that's much simpler called put forks that merely sets the right and left to be the specified right fork and left fork. So this is used when a philosopher is done eating and you put their forks back into the placement. The setup table creates a table of a specified size. It has a helper function that makes a fork with this specified index and sticks it into a sum inside the tref, because the initial state of the table will be, all those options will be sums around the entire table containing forks. That's the way the problem starts. How we do this is we call stm for each on 0 to size. So we iterate over all the numbers from 0 to size. And for every number I, we make a fork I. And then ZIO for each will give us back a transaction that succeeds with a list of trefs of options of forks. And then we have to actually link all these up. So we have to, in every placement, we have to actually specify 2 forks. So the easiest way to do that is to take all these forks and to concatenate the one at the very beginning of the list, because that will allow us to pair all forks with dropping the first one of all forks. And that allows us to make sure that we're lining up every fork with the one that's right next to it, including that at the very end will be aligned with the first fork here. The very end will be aligned with the first fork in the list. So it wraps around, the table wraps around. And then we map this left and right tref to a placement that contains the left and right tref. And finally, we yield the round table. And then all this gives us back a transaction. Eventually, we have to commit the transaction. And when we commit a transaction, we convert from STM data type, that's the transaction data type, into a ZIO effect. And this is done in an atomic fashion. It's also consistent, isolated from other transactions. And we don't have to think about locks. All we have to do is think about what we want to happen in the same transaction. And when we're ready to execute that transaction, we just call commit on it, and it commits it atomically. The eat method here is designed to run the logic of the specified philosopher around the round table. And what it does is it takes the forks, and that gives it a transaction, so it commits that transaction. It prints out this message that the philosopher is eating. It puts the forks back, commits that, and then it prints out this other message saying the philosopher is done eating. And finally, the run method, which initializes a table that's that big, and then calls this helper function, which creates all the eaters, 1 eater per philosopher, just calls e here. And then it forks off all these eat effects into a single fiber, and then joins that fiber down here. Join will await until the fiber succeeds or fails. And then the success or failure will be propagated in join. In this case, the fiber cannot fail, and it just succeeds with a list of unit representing the individual units that are returned from the eat of every philosopher created in here. So this won't return until all the philosophers are done eating, and then after they're all done eating, we print out a little message. So as you can see, this is fairly straightforward. The deep magic here, the hard part of this problem, is in take forks. Because what we want to do is we want to acquire both forks. We need both forks. And STM provides a really simple, elegant way to do that. If we weren't using STMs, if we were using locks, then we would need to have a lock around this and a lock around this. And then we would have to lock them in some sort of order, being sure to avoid deadlocks. We have to use condition variables because we might lock this one and then check inside it and see it's empty, in which case we can't take both forks, so we have to wait until the philosopher to our left ends up returning their thing in their fork onto the table. And then we would similarly check this one, acquire a lock and check it, and then maybe it's not there, so we would have to use condition variables. We would have to signal those condition variables every time we made some modification to them to wake up everyone who's sleeping on them. it would be a gigantic amount of low-level mechanics. And we don't have to do anything of that with STM. We just open up a for comprehension, and we call left.get to get out the value of this, which would be an option of a fork. And then what we do is we match against this left option, and it's going to be either none or a sum of a fork. If it's the sum of a fork, we'll return stm.succeed, which is similar to ZIO succeed, with that fork. And if it's a none, well, what do we do here? Well, what we really want to do is we want to, in essence, roll back and wait until someone else comes along and modifies this tref, and then maybe try again. And we can do that using the stm retry operation. So what will happen is when we hit this retry case, if we do hit this retry case, the entire transaction will be rolled back, and this will be suspended asynchronously until some philosopher comes along and modifies this left-hand side. And when they do, then the transaction will be retried automatically, and it gets a chance to see if there's a fork in there now. This allows us to make sure we have the left-hand side. However, we need to do more than that. We need to repeat the logic on the right-hand side to make sure we have the right-hand side. I'll just copy-paste this, and then I'll show a better way to do it later. So here we have right option on right, and right fork on right option. And now what will happen is maybe we acquire this one, and then we get all the way to here, and we see, oh no, it's none, and so we have to retry, and so forth. But eventually, we're going to acquire the left one, and we're going to acquire the right one, and then we're going to be able to end up succeeding with the left fork and the right fork. Now, there's a much simpler way to write this. We can actually call this method collect, which is available on any STM transaction, which lets you specify a partial function. And what happens is if your partial function is defined, then it maps whatever was inside the transaction into this value. And if it wasn't defined, it will retry. So it will suspend the whole transaction until someone modifies this variable that was accessed here. And when that happens, it'll retry it. So eventually it's going to end up succeeding, and you're going to get the thing out that you were looking for. And this allows us to tremendously simplify all this logic. Not that it was that complex, it was just a little tedious, ugly to write. You can get it down to something like this. And this can be further simplified because we're taking two effects and we're basically producing a tuple of their successes, and that operation can be done much more simply using zip. That's what zip is intended to do, zip two effects into a single effect. And at this point, we've reduced the hardest part of this problem down into a one-liner. We just pull the fork out of here, we pull the fork out of there, and we return it as a tuple. STM really is that powerful. It takes very hard problems and it makes them super simple. You can use it to define all sorts of really interesting things like caches and complex finite state machines that are concurrent, and metrics counters, and virtually anything you can imagine, reentrant locks and so forth, rate limiters and so on. Now STM is 100% asynchronous. It's non-blocking. Nothing ever blocks, so you don't have to worry about even things that look like they're blocking. They're not. And there are no spin loops. So the retrying here that I mentioned that happens in these cases here, if the conditions aren't satisfied, is 100% asynchronous. And all the effects that you get back from committing transactions can be interrupted by using the ordinary interrupt method that we already saw, which you get access to when you fork an effect It's called in other times as well, like when you time out an effect or do something like that, ZIO will interrupt things. In our final example, what we're going to do is actually create a type of actor. Our actor is going to be nothing more than a function. It's the ideal type of actor. Given some command, it returns an effect that succeeds with a double in this case. So our commands will be read temperature and adjust temperature. And read temperature is going to give us the current temperature. Adjust temperature is going to adjust the temperature. And we send messages to this actor by calling the function. That's how we send it messages. And if you like actors, there's a project called ZIO Actors you can investigate that allows you to have typed requests and responses that allows you to achieve quite a bit more expressive power than a simple function like this would let you achieve. Anyway, our function that we're going to implement is called makeActor. It's going to create an actor. And the actor will initially be initialized to this specified temperature, and then it's going to return the actor, and then the makeActor function will be called here. And in parallel, it's going to be sent a whole bunch of different messages saying to adjust the temperature. And then at the very end, we're going to read the temperature out, and we're going to print out what that temperature is. So to make the actor, we're going to utilize a ref to hold the actor state. We're going to utilize a promise to do some work handoff between fibers. And we'll utilize a queue because every single actor, doesn't matter the language or the paradigm or whatever, every actor has a queue. It's a mailbox of incoming messages, work to process. So the first thing we're going to do is make a ref. And this ref will hold the state of the actor, which will be the current temperature. And then what we'll do is make a queue, and we can do that using queueMake. It's going to have type a bundle here. I'm going to construct a bounded queue with a bound of 1000. The bounded constructor gives me a doubly back-pressured queue. So if I put too much stuff into the queue, then the producer will be suspended until there's room. And queues are always back-pressured on the take side as well, on the consumer side. So if you take from an empty queue, that suspends until someone puts something in the queue, and then it resumes. So this queue here is totally asynchronous. It's non-blocking, and it's concurrent safe. Once I make my queue, I can now create the logic for my actor. Note here carefully what the queue is going to contain. It's this tuple. It's going to contain a bunch of tuples. Every tuple is one of these commands together with a promise to return some sort of response here. And this is how we're going to do some handoff between whoever's calling the actor and the logic inside here, which is going to execute the logic of the actor. So our actor logic is going to take one thing off the queue, and then it's going to flat map that, so it's going to do something with that. And we get a command and a promise. But actually, there's only two commands, so I'll inline them. There's read temperature command. And in this case, all we have to do is get that temperature from the ref, and then flat map that to promise.succeed, which will complete the promise with the specified value. And then the other command is adjust temperature by the specified delta. We'll call ref update. We'll add the delta to it, and then we're going to take the new updated value that we get out of there, flat map that to promise.succeed. And then we don't want to just take one thing from the queue. We want to keep repeating this process forever, so we'll call forever. But also, we don't want the main fiber here to get stuck in this queue loop, so we'll fork this off into a separate fiber. And now we have the actor logic executing in a separate fiber, continuously taking things from the queue and doing stuff in response. And then finally, we're going to yield here our temperature actor, which is this function from command to an effect producing the response. And how we're going to make that is we're going to accept a command of type C, or of type command. And the first thing we'll do is we will make a promise. And then we'll take that promise and we're going to put the promise and the command as a tuple into the queue. And then what we'll do is we'll wait until that promise has been completed. So we call p_await to do that. And then that will give us back our double. So this function here that we're yielding, it takes every command and it makes a promise, and it takes that promise together with the command, bundles them up into a tuple and stuffs it in the queue. And then after it does that, it's just going to sit back and wait until the actor has a chance to process that message and complete the promise. Obviously, all of this, like the rest of ZIO, is 100% asynchronous, so there's no actual waiting involved. All this happens very efficiently. And there we have it. We have a actor re-implemented, the actor model re-implemented using a few tiny little constructs in ZIO and a small amount of code. And obviously, if you like this style of programming, you can use ZIO actors or build your own machinery. But it's a real testament to the fact that actors are not fundamental. They're not a fundamental abstraction. ZIO's primitives allow you to build actor things, but allow you to build a huge variety of other things with benefits that you can't obtain from actors, such as composable transactionality and strongly typed errors, and many other features like being able to define combinators on things, combinators on effects that accept and return effects and retry them or repeat them or do something else with them. There's a whole world of possibilities out there when you switch over to a functional effect system. And I hope this video has given you a sneak peek and maybe inspired you to go out there and learn more. If you're interested in learning more, then please head over to zio.dev. There's some great resources there, and keep an eye open for upcoming videos, talks, workshops, and an official ZIO book.